Alright, we're going to take a look at how to set up a simple buckling problem in SOLIDWORKS analysis. This is just going to be a round column with a 2-inch diameter, 100 inches long. The end conditions are fixed on one side, free on the other, which produces an effective length of 2 times the raw length, so 200 inches. Calculating cross-sectional properties, and you've got Young's modulus about 10e to the 6. This is an aluminum alloy. And we're calculating the transition slenderness ratio and see that we're well above that, meaning that the Euler buckling value should be pretty accurate. So just under 2,000 pounds. I've modeled this in SOLIDWORKS as a solid 2-inch diameter cylinder. And under simulation, I'm going to create a new study in buckling. And we'll have to create all the boundary conditions. If you already have a static analysis defined with fixtures and loads and that sort of thing, you can copy some of that information over into the buckling study so you don't have to redefine everything. And we can take a look at how to do that in one of the bicycle models in the near future. So I fixed one end. On the other end, I'm going to put an external load, a force. And I'm going to give this a value of actually 1 pound. The reason for that will become apparent when we look at the results. So that's the basic setup. I'm going to need to define a material on this, and I do want an aluminum, so let me go into materials. I'm just going to grab some alloy that I'm at least familiar with. 2024 T4, that works. This should be ready to run. We'll say if you right click on the actual buckling case and go to properties, you can get results for multiple buckling modes. The first mode is what you would primarily be interested in, but we can take a look at a few of them. This runs pretty quick. That should not have made any difference. It should have just done that. I'm not sure why it didn't mesh automatically there, but there we go. So there's our first mode. The amplitude resolution, we're not going to look into that right now. The main thing that you're viewing in these results is up here in the title block. The fourth line, there's this entry that says load factor. In this case, it equals 2037.1. What that means is relative to the applied loads, it can handle 2037 times that applied load. And since I applied a load of 1, that means that the actual buckling critical value for this is being predicted as 2,037 pounds. And if we take a look at the hand calculation again, we got 1,937. So it's off by about 100 pounds relative to the hand calculation. That could be due to meshing. It could be due to the way that this load's being applied. It could be due to a few different things, but regardless, it's a pretty reasonable approximation, and you get there really quickly. And again, if you have a more complex model and you've already defined load cases in static analysis, you can actually I can show real quick. If I just create a new study, we'll make this one static. If I want to transfer, say, the boundary conditions from the buckling analysis to the static, I can actually just drag those to the new study and it applies them automatically. So that can save you a lot of time, since I know a lot of you have already set up the static load cases in your analysis models.